Start with good old 6.1. This is where your whole life's about to change. Yes.
Oh, no way.
You're going to learn the third main idea finally. It's integrals, but you don't even know what an integral is yet. We're going to start with just Riemann sums.
I do. Just kidding.
This is Riemann. It's okay. So what that is, we'll do a few of right now.
Oh, how do you see mascara in Spanish?
We're going to start with an elementary school problem.
Sweet.
You ready?
5 plus 2.
No, a little harder. A train moves along a track at a steady rate of 75 miles per hour. Okay. Got a train going along a track at 75 miles per hour. We can write this down. So the train's going 75 miles per hour, and it does this from 7 a.m. to 9 a.m. Almost changed it to way harder. What is the total distance traveled by the train? Anyone have an answer? Yeah. There you go, 150 miles, right?
I put PM, not AM.
I almost did too.
That's why I was like 75 times 12.
No. Just moves. How did you get that, Pedro?
75 times 2.
Why'd you do 75 times 2? Because you know distance equals rate times time, right? Right. Because you know that, so you just 70 miles per hour times 2 hours is 150 miles. Cool. Whoopity-doo. Well, that's simple. But now suppose that you are Isaac Newton. That's what it says in the book.
I'm not.
Now suppose you are Isaac Newton trying to make a connection between this formula and the graph of the velocity function. So here's where it gets good. Let's graph the velocity function. So in the case of our train,
The
we're going to
derivative?
t. Well, it's the derivative of position, but we don't have a position function. So all we have is v of t equals 75, because it's just constantly going 75 miles per hour, right? So my graph would look something like. And I'll just start right here with 7 a.m. Here's 8 a.m. Here's 9 a.m. I'm going to go, here's my velocity. It's 75, and it's just constant, and then the train stops. Right? Well, there's a huge connection between this graph and this answer. And I'll just tell you what it is. Check this out. If we go from 7 a.m. to 9 a.m., and then the velocity is 75, we know we went 150 miles, right? But the way we can do that, just looking at this graph without having to know this, notice if I make a rectangle here, what would the area of this rectangle be? How long is this side?
75.
This side is
2.
2. This side is 75. What's the area of that rectangle? 150. That's no accident. That'll happen every single time. Even if your velocity, if you're Sir Isaac Newton, you could prove this, but you don't need to. Even if your velocity is some crazy curve, like if you can find the area under there, it'll tell you how far you went. If this was velocity and this was time, if you could find the area underneath that curve, it tells you how far you went. So we're going to be finding a lot of areas under curves to begin with, because it's very useful for position, velocity, and acceleration. And we'll connect it to an integral later. An integral is actually doing area. We're going to do lots of areas under curves, long story short. Okay? That'll happen every time. So let's do a different one. something like let's say you've got a velocity function, v of t equals t squared plus 1. So your velocity is t squared plus 1, so it depends on your time, right? This is a constant. Your velocity is changing over time. We're going to find how far you would travel, or we're going to approximate how far you would travel. In 6 hours. So we'll say t is 0 to 6. So this isn't just a simple 150 or 75 times 2, right? It's not 75 times 6, because your velocity over the time is changing. So this is going to be more like this case. So we're going to have to find the area under a curve. And the reason I say approximate is because right now we don't know how to do it exactly. But we can approximate. You know how to draw that? It's a parabola. But it's only half, right? Because we don't need the negative regions.
Yeah.
That would just be a parabola shifted up 1, right? We'll start at 1. And then it's just going to be a half of the parabola. I'm going to draw it nice. So there's 6. Ooh, no, okay. Even the space there. 1, 2, 3, 4, 5. Pretty close. Well, how can we find the distance we traveled? We can do the area under that curve.
3 times 9.
So how can we find the area of that thing?
Find the area between each, I don't know,
Between each what?
little points, I don't know.
You're right. We're gonna break it up into a whole bunch of small rectangles. Because if we can break it up into a whole bunch of rectangles, don't we know how to find the areas of rectangles really easily?
Yes.
So we're actually going to do this same problem 3 different ways. You're going to have what's called the left, I forget the actual name. This whole idea is called the rectangular approximation method. Basically, we're going to draw a bunch of rectangles. So what I mean by that is, I'm going to put a rectangle like this under here. I'm going to put another rectangle like that. Put another rectangle like that. Another rectangle like that. Another rectangle. And then another rectangle. I don't know. So if I could find the areas of all those rectangles, wouldn't I have a fairly close guess? I mean, I'm missing like that area, that area, that area, that area, that area, and that area. So is my approximation going to be too low or too high?
Too low.
Too low. This is called the, well, the book calls it the LRAM, left-hand rectangular approximation method. The reason I say left-hand is because notice on each of my intervals, 0 to 1, 1 to 2, I went up on the left till I hit the curve, and then I drew the rectangle. There's another way you can do it. And draw the same exact thing. There's the T again. And there's 6. So in this case, we assumed our intervals were 1 hour. We could have made our rectangles smaller. We could have made the bases of them smaller and only gone like half an hour for each rectangle. And the smaller you make your rectangles, the more accurate you'll become because you'll have less space. Yeah. Because if you made like a whole bunch of smaller rectangles, you'd have go up. Okay. But for this one, we're just going to do the intervals are 1. So this was the left hand because on each interval, I started on the left, then I went up till I hit the curve, and then I went over with my rectangle. On this one, we're going to do the right hand rectangular approximation method. So the only difference is, now for this rectangle, I'm just going to go to the right and go up till I hit the curve and then draw the rectangle. So I'll start on the right and I'll go up till I hit the curve and then draw the rectangle. For this one, I'll just go on the right up till I hit the curve and then draw the rectangle. Do you see the difference? Right. 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 What's going to happen with your approximation on that one? It's going to be over, yeah. Told you there's 4 different ways we're going to do this.
You said 3?
There's actually 4. 3 today. Well, if this one's under and this one's over, how could we make it better? How could we get more accurate? Oh, use this one and this one and take your answers and subtract them? Okay. Well, how could we do it just one way and make it more accurate than either one of those?
Just go up to the line.
This is left hand, this is right hand. We're going to have one that's middle. So on this one, I went on the left and went up till I hit the curve. This one, I went on the right and went up till I hit the curve. On the third one, you're just going to go in the middle and go up till you hit the curve. So let's draw that one. So exciting. We're actually going to calculate it here in a second. One. There's my parabola. 1, 2, 3, 4, 5, 6. So we're still doing 1 hour intervals. My rectangles are still going to have a base of 1 hour. But now, I'm not going to go up on the left till I hit the curve. I'm not going to go up on the right till I hit the curve. I'm going to go right up the middle till I hit the curve and then draw in the rectangle. That one you can't really see what's happening, but hopefully it works out to where we can actually see. So what's happening with each rectangle?
Getting a little bit of all from each side.
Yeah, you're getting a little bit above and a little bit below, right? Middle. So, just to recap there. 3 different ways of doing it. It all just depends. First thing you have to know is how big you want your intervals to be. In this case, we just did 1 hour. We just drew a rectangle for each hour to approximate it. This one's called n. And that'll tell you, in the problem, it'll tell you how many, they'll call them sub-intervals. It'll tell you how many to use. So in this case, I would say, how far would you travel in 6 hours? Use 6 sub-intervals. So that means each interval is 1 hour. So each rectangle is just 1 hour long. So you know each one's 1 hour. So if you do left hand, you go on the left of each one and go up till you hit the curve and then draw the triangle over. Triangle, rectangle. Here's this one, so I start on the left, go up, hit it, draw it over. Here's this one, start on the left, go up, right? The right hand one, you start on the right, go up till you hit it, and go over back that way. And then the middle one, you got to go in the middle of each interval until you hit it. And then you'll have a little bit above and a little bit below. So in all three cases, if we just add up all the areas, isn't that pretty close to the area under the curve? So let's do that. That makes sense? Do you understand how if I made the rectangle smaller, it'd be more accurate? What if we made them infinitely small? We would take the limit as the width of the rectangle approaches 0? Holy shnikes, that sounds familiar. Oh, we'll get to that. For today, we'll just go with this.
Thanks.
We'll make our approximation like exact almost by doing that. But okay, so how are we going to calculate all the areas of all these things? Do you know? Well, what's the width of all these rectangles? 1.
We need to figure out.
So isn't the
height.
area just going to be
How
1
tall
times
is-
whatever height is? So isn't the
Yes.
area just the heights of all of them?
Yeah.
All right. So we're just going to add up all the heights of all of them basically for this one.
Is
What's
it just
the-
one?
Yeah, it'd be like one.
The height of that one is 1. But what's the height of that one?
Oh,
Uh-oh.
like 1 point something.
2/1.
I don't know. How could we find out?
Are you gonna have to do a little?
2/1. Just kidding. I
Plug
don't
it
know.
into the calculator.
Plug what into the calculator?
T squared plus 1.
Oh, hey, this
Stupid.
curve is t squared plus 1. So if t is 1, what's this point? 1 comma 2.
2.
1 squared is 1 plus 1 is 2.
Oh.
So how tall is my second triangle?
2.
2. Plus, how tall is my third triangle? Or I keep saying triangle. They're not triangles.
And then we're just like, yeah,
Rectangle.
yeah.
I know.
We're not, but if Shania would have been here, she'd be like, triangle.
Five. 5.
Is it 5?
Yeah.
2 plugging 2 squared
That's a
4.
good thing.
That one's 5,
She
yeah.
keeps them on check.
Shut up.
So that one's 5 tall. 3 squared plus 1 is
Shut it up.
10. 4 squared is 16 plus 1 is 17. 5 squared plus 1 is 26. Do I need to do 6 squared plus 1?
No.
No, because there's no rectangle over here. Hey, I got it right.
Okay.
The last rectangle is right here. Because if I drew one up to here, that's way over, that's not under my curve. So I get 1 plus 2 plus 5 plus 10 plus 17 plus 26. What's that? 38, 18, 35, 61. So your answer would be, how far would you have traveled? It depends on our units. I don't know. We'll say miles. That would be your distance traveled.
Are we gonna start doing like crazy stuff with this? Are you gonna throw like pie stuff? Oh, okay.
So, can you do this one? What's the height of that first rectangle?
1.
Plug in.
Plug in 1, 2. Right? So you'd have 2 plus 5 plus 10 plus 17. Ooh, where'd I get those? Just plug in all these,
You
right?
just forget the first one.
So if I plug in 1, I get 2. Plug in 2, that height would be 5. Plug in 3, that height would be 10. Plug in 4, that height would be 17. Plug in 5, that height would be 26. But then I also have to do this one. So plug in 6. 36 plus 1 is 37. Add those all up. What do we get? I don't know. It doesn't matter.
97.
Huh?
Is it 97?
Oh, subtract 1 and then add 37. Yeah. Good job. 7 miles for that. So that's too low. That's too high. Let's do the third one and we'll have an even better approximation, right? This one's not as easy though. The base of the rectangles. The base of the rectangles is still 1. So again, I just need the height. But now finding the height's kind of pain in the butt because
You gotta go halves.
You gotta go halves, yeah. So I've gotta plug in a half to the equation. Half squared to fourth plus 1 is 1 and 1/4, or 5/4.
I hate fractions.
Plus. Do you understand the point?
Yes.
Yeah.
Okay, we don't need to do it. You would plug in 3 halves, squared it, 9/4 plus 1 would be 13/4, plus on and on and on.
I'm guessing the answer would be in the middle
Yeah, in
of
the middle.
61 and 97.
Maybe we should actually do it.
Yeah. It is?
I don't know that it'll be exactly in the middle, maybe. Let's just do it real quick. I'll do it fast. I have most of them written down. 13/4, the next one's 29/4. I don't know the next one though. I just did dot, dot, dot. As long as you understand the idea, the answer doesn't really matter for this one. We'll see. What's that? 3 halves, that'd be 3 halves, that'd be 5 halves. Did that one. That'd be 7 halves. Squared is 49/4, so 53/4. And 9 halves squared, 81/4, so 85/4. And that would be 11 halves, 121/4, 125/4. Hey, they all have a common denominator already, that's nice. That's 18, 47, 185, 285, 305, 310/4. This could be wrong, I'm just going fast. It's 310/4, 4 to 310. 80? No, that's 320. 70, 280, 30 more, so 7, 28, 280 and 28, it's 308, 77 and a half.
Yeah.
Is that right in between those? 97 minus 61 is 36. Divided by 2 is 18. 61 plus 18 is 79. Nope, it's not exactly right in the middle. I didn't think it would be.
Just a tad.
It's not, it's a little tad off. But that is the most accurate answer out of those. It's still not exact, but at least on this one I had a little bit above and a little bit below. Think you could do that if I gave you a different function and you could do the left, the right, and the middle?
Maybe. Depends on the function.
What if the function was
No, I can do it.
2x minus x squared?
Maybe. I think so. It's gonna be upside down.
That's your mark problem. 6.1. Lost my little. Quick review, numbers 1 through 4, and regular 6.1, numbers 5 and 6. So don't be confused here, it's not 1 through 6. It's quick review 1 through 4, then go to the regular problems and do 5 and 6. And 5 and 6 is doing these 3 things.
What page is this on?
Oh, wait, no, it's not. 274. So like number 5 says, A, sketch the region R. Well, it tells you your function is y equals 2x minus x squared, and you're going from 0 to 2. So the first thing you have to do is draw that. Upside down half per up. I would plug in some points. Right? Because it might be shifted weird. Like how far up? I don't know. How far, you know what I'm saying? If I plug in 0, what do I get for y? 0. Plug in 1. 2 minus 1 is 1. That's weird, it's went up. Plug in 2, 4 minus, it's back to 0. So it is an upside down parabola, but it's right there like that. So then when you draw in all your rectangles, you might think, well, there's only 2 rectangles. Well, no, because it says, part B says partition 0, 2 into 4 subintervals. You know what that would mean? Yeah. So you're going to have 4 rectangles. You're gonna have half, from half to one, and then from one to one and a half to two. Can't talk today. I can try this. So show the four rectangles, let's do it again. The LRAM and do LRAM. So it's basically you're doing this one, left, right, and middle. Same function, 4 subintervals. Just doing it. That's it. Start easy on day one. Approximate.
So when you do the half one, you're gonna have to do like half of the half.
Yeah, so that's a good question.